Yes, I was at Science Field Day, too.
Whose dad are you?
Well, like Ms. Krishnan said, I'm Dr. Ed. I'm a chemist by trade. I'm going to show you some fun today with chemistry and with physics. Okay? Question?
Whose dad are you?
Huh?
Whose dad are you?
Alice Schweiger.
Sixth
Oh,
grade.
I know her. Alice? I know her. She's birthday.
Okay. We're going to start off with, what are these?
Candle.
Candles, exactly. What can you tell me about a burning candle? What can you tell me about a burning candle? Yes.
Why did you go this way?
Well, what we've got going on is what's called an oxidation reaction. We've got the wax, which is the fuel, and the fuel is combining with the oxygen in the air to give a flame. And it's a rapid chemical reaction, lots of heat. Okay? It's also similar to the chemical reaction that goes on inside your body when your body uses oxygen and the food you eat to generate energy to run your body. Now, they're very different rates. In your body, the oxidation takes place relatively slowly at a lower temperature. It's very highly controlled. When you get up to a candle, you've got a very rapid reaction, lots of heat given off, still relatively controlled. If you go up to an even higher speed of the reaction occurring, you can get an explosion. So something like candle wax is very similar to gasoline. Gasoline in a car engine explodes when you mix it with air and hit it with a spark. Okay? So it's all a difference in how fast the reaction occurs. In a flame, it's sort of a medium speed, and it's an oxidation reaction. Now, can anybody tell me what happens when you mix vinegar with some baking soda that I have in the bottom of this vase?
It's like a volcano. It shoots out.
Well, it may not shoot out. Depends on how fast the reaction is. Again, it's a question of how speedy it is. Okay.
It's all bubbly and
It gets bubbly. Now, can anybody tell me what those bubbles are that occur?
Carbon dioxide.
Exactly right. Come on, raise your hands, though. That is correct. Carbon dioxide. Now, remember we said that the chemical reaction that causes the candle flame is the wax combining with oxygen, right? Now, what do you think happens when I pour a bunch of vinegar in here and the carbon dioxide is generated from reaction with the sodium bicarbonate? Yes?
The flame goes out?
Well, only a few of them have so far, right?
Oh, yeah. Yes.
Does anybody have a guess as to what's happening and why they're going out in that order?
Shh, you're raising your hands, guys. Lauren.
Exactly. What happens, carbon dioxide is being generated in the bottom of the vase is actually denser than air. Okay, so it'll tend to sink down in air, whereas helium would go up. Okay, so the carbon dioxide slowly fills up the chamber, and as the carbon dioxide fills up, it displaces the air that's present in there. Okay, without the air, there's no oxygen for the candle flame to burn anymore. You can't have the oxidation. Now, oxygen gas in the air isn't the only thing that can act as an oxidizing agent. There are also chemical compounds that'll give up their oxygen atoms to other compounds and cause an oxidation. Okay? One such compound is called permanganate. Now, I've got a vial here. This is water with some permanganate dissolved in. Okay? It's kind of a purpley green color. All right? And what happens, this material, like I said, is capable of giving up its oxygen atoms and undergoing a chemical change. What I have here is glycerin. Okay? So this is glycerin and permanganate in water in this vial. Now I want you to remember these two chemicals because I'm going to use them later today outside. So glycerin is sort of, it looks a little bit like pancake syrup or maple syrup, except it's clear. So we're going to add some to this. Glycerin can be easily oxidized. And remember I said permanganate is something that can oxidize other compounds. So the glycerin and the permanganate can react together in water. Okay? And if you look, you may be able to see the bottom is sort of a bright green now, and the very bottom is sort of a brown, because the glycerin is dense and sinks to the bottom, just like the carbon dioxide was when it was staying on the bottom in the vase. If I mix this up, and we watch it over the course of a few minutes, you see the color will change as the chemical reaction occurs. Okay? So the permanganate is giving up its oxygen atoms to the glycerin, and then the glycerin is being oxidized, just like candle wax in a flame or food in your body with oxygen would be. Okay? And over time, as we watch this, you'll see it'll probably turn into like a pale brownish color. And all the permanganate is now gone. It's transformed into something else that no longer has the purple color. Okay? So that's an oxidation reaction. Like I said, we'll see this oxidation reaction later today also. Because I'll take permanganate and glycerin, and I'll mix them together, but I won't use any water. Okay? Now this water will warm up a little bit from the reaction of the permanganate and the glycerin. Okay? But the water helps moderate the reaction. Okay, it'll help with absorb some of the heat so it doesn't get out of control. Yes?
Are you trying to do nitrogen?
No, not trying to make nitroglycerin. That's different. Now that's an explosive.
Yes,
That-
exactly.
Explosives in general, something like gunpowder, actually has a fuel and an oxidant mixed together. Okay, but they don't react until you set them off with a spark or a fuse or something like that, or a shock. Okay, so that's a combination of a fuel and an oxidizer, just like you get when you mix gasoline and air inside an engine, or if you mix air with a candle flame, with the hot wax from the candle flame. Those are all oxidation reactions. They just occur at different speeds. An explosion is really fast, and when you get an explosion like that, you're taking those solid materials, or in the case of nitroglycerin, a liquid material, and you rapidly convert it into gas. Who can tell me the difference between the volume of a gas and a liquid? Does anybody know? Yeah? Okay, yeah.
Well, liquid, their molecules slide over one another. Gases, their molecules are more separated.
They're more separated, exactly. If you take a gram of water, okay, which would be like a cubic centimeter, all right, that's relatively small. 1 cubic centimeter is small, it's a milliliter. But if you take that same gram of water and you bring it up to about 150 degrees so that it converts to a gas, it'll convert it 100 degrees to a gas, you end up with a lot larger volume, okay? A gram of liquid water is small. A gram of air or a gram of steam is very big. It takes up a big volume. So an explosion is essentially causing a solid or a liquid, okay, by some chemical means, to change from that solid or liquid, which is very small, to a gas, which is very big. When it takes up more space, it moves out. You get an explosion, as long as it happens fast enough. Now, an explosive like gunpowder, the reaction's really fast. You get a rapid change and a big pressure change. With a candle flame, you're controlling the reaction. You're burning small amounts of fuel with the air at a slow rate. In your body, you're burning your fuel, your food, with oxygen at an even slower rate and a lower temperature. Explosions are extremely hot. Candle flames are hot. Your body is sort of warm. Okay? Different speeds of the chemical reactions. Now, something else I want to talk about today is pH. Can anybody tell me what pH is? Okay, do any of you have a pool? Okay, you know the little test kit you have with the yellow and the red things? When you test on the yellow side, that tests for chlorine content.
Oh, yeah.
On the red side, you're testing the pool's pH. Now, pH is a measure of acidity, okay? Things that have very low pHs are acidic. Things that have very high pHs are basic, okay? Now, the pH scale runs from 0 to 14. 7 is right in the middle. Water, pure water is pH 7, okay? And then something like hydrochloric acid, okay, has a very low pH. It's one of the strongest acids you're going to get. So let's say hydrochloric acid is down here. Okay, it's acidic. Up at the end of 14, where we have strongly basic compounds, we'll have something like, for example, sodium hydroxide, NaOH. This is basic. Okay? And it has to do with how many acid molecules are in the water, the concentration of the acid molecules in the water. Now, one of the ways that we can measure the pH, one of the ways is with an instrument. With an instrument, you can get really accurate measures of the pH. One other way that we can do it is with something called a pH indicator. Now, a pH indicator is a special type of molecule that undergoes a chemical change somewhere along here, okay? And on one side, it'll normally be a given color, and then on the other side, it'll be a different color. So if we adjust the pH through the range where the compound will change color, we'll see a color change. And that'll tell you that the pH has changed. Okay? I have one such indicator right here. This is called bromethymol blue. Now, in its natural state, this is a magnetic stirrer. Some of you guys may not have seen these before. You can have these plastic-coated magnets, okay? There's a magnetic bar in here, and then there's a motor with a magnet on here. The motor spins the magnet, and the magnetic field will go through a glass flask like this and stir the mixture. Okay? This is bromethymol blue in its natural state. Bromethymol blue, as its salt, is naturally sort of a greenish color. Okay? This is hydrochloric acid, all right, in a dropper model. Hydrochloric acid, strongly acidic, pH 0. So as I add hydrochloric acid to this mixture, this is probably around pH 7 or 8, something like that. It's got bromethymol blue in it. It's not pure water, so it's not going to be exactly 7. As we add acid to this, okay, a chemical reaction takes place. right? And the bromethymol blue, which is naturally green, goes through a color transition when we move down towards the acidic side of the scale. Okay? So we know now that bromethymol blue, when you make it acidic, is sort of a brownish yellow color. Right? If we go back the other way and we start adding a base, this is sodium hydroxide. Again, this is pH 14 on the other end of the spectrum. If we add a base to this mixture, okay, the base is going to react with the acid. Acids and bases react together to give water. Okay? So once we've added enough base to use up all the acid, then the pH will move over towards the basic side. In other words, the sodium hydroxide will sort of win out because you put more of it than there was acid. So as I add the base to this with it stirring, you'll see the base will react with the acid, okay, and it will give us a bright color change. So bromethymol blue, when we get towards the basic end of the scale, gives a deep blue, sort of a royal blue color. And this is reversible. If we go in and we add some more acid, okay, to use up the base, the pH is going to shift the other way again. And the pH indicator will just shift back and forth as I add it. Okay? And we'll go back and forth. Now we're on the acid side, right? And then we can go back to the basic side, have a drop or two. And we'll go deep blue.
That's cool.
Right? And then back to the acid side.
Whoa.
Now, you wouldn't know from the observations here, but I'm going to tell you that the pH range where bromethymol blue changes from that yellowish color to a blue color is probably right about in here, like between maybe 7 and 8.5. Okay? And on this side, like we said, it's essentially yellow, and on this side, it's blue. Okay? So that's the bromethymol blue. Let's call that BR blue. Okay? I have another type of pH indicator here, and it's in this flask. Okay? This material right now is going to be probably around pH 5 or 6. It's a little bit below 7. Okay, it's not pure water. It's got something called phenolphthalein in it. All right, and it's slightly acidic right now. Looks like water, right? You don't really see anything. I know it's on the acidic side, okay, because I added a drop of acid earlier, and it's clear. Now, this one, we're going to go from the acid side, probably right around here where it is now. I'm going to add sodium hydroxide and bring the pH to higher numbers. We're going to make it more basic.
Whoa. Whoa.
Okay, so as you add the base, on the basic side, it goes to like a purpley magenta color. All right, and I happen to like that color. It's really pretty cool. Okay, so that's on the basic side. Again, you wouldn't know it from these observations precisely, but I'm going to tell you that phenolphthalein has a transition range somewhere in here. Okay, where it goes from clear, okay, or colorless, over to, let's call it red, even though it's more like a purpley magenta. Okay, so this is phenolphthalein. I'll just call it PHTH. It has a really complicated spelling. But, so we go from clear to red. Now, what I'm going to do, I've got a larger flask here. Okay? We're going to take this mixture. Okay? I'm going to add, let's bring this back so that it's clear. Bring it back to the acid side. Okay? And then we're going to add it to this large flask.
Does that spinny thing
I'm going to put one of them in. If I put two in, it's not going to work very well. They kind of fight with each other. Okay, so now we got a larger flask. Settle down. There we go. Okay, now remember I made both of these acidic. So now we're down here. The bromethymol blue is yellow. The phenolphthalein is clear. Okay, on the acidic side. Can anybody predict what's going to happen when I raise the pH? Yes? It's going to turn purple. Okay, that's fine. So if I get about here and the bromethymol blue goes from yellow to blue, it's going to turn purple.
Oh, no, wait. When it's along the basic side.
Over here?
Yeah.
Okay, so what's going to happen in between? Okay, well, let's find out. Base. Right. We're on the acidic side. We're going to add base. We're going to bring the pH up.
Whoa. I can't see it.
Now, that's just because of mixing in the larger flask. The acid and base sometimes take a little time to react together. So in this case, the base reacted with all the acid. There's still a little bit of acid there, so the pH is still on the acidic side. So we still don't have any color.
Whoa.
One more drop.
Oh, I like that blue.
Okay, now, based on what I know about these two pH indicators, I'm gonna say the pH is like right about here. Okay? We've gone past the point where the bromethymol blue goes from yellow to blue, but we haven't got to the point yet where the phenolphthalein goes from clear to red. So, if we go farther on, we had a prediction from the audience earlier that if I did this, it would get more purple.
Kobe.
Now, the bromethymol blue might be a little more concentrated than phenolphthalein, so it may be sort of a
Do
bluish
both of
purple,
them
but
at the same
the
time.
phenolphthalein pink comes in and gives you a color like that, which is more like a royal purple. Yes?
Do both of them at the same time.
Do both what's at the same time?
Acid and acid and
No, because they'll just react and cancel each other out. If I were able to get the exact, these pH is very sensitive to the amount of material in there. If I was able to take exactly the same amounts of sodium hydroxide and hydrochloric acid, I would be able to get pH 7. Okay? And at pH 7, it would just be yellow, below the transition point for both of those. Okay? If I were able to do that. But since it's so sensitive to slight excesses one way or the other, you can't really get it to pH 7 in this kind of a state. And if I did add both at the same time, they would react together, and whichever one was in excess would win out, and the pH would go that way. That's essentially what I'm doing by adding base and then adding acid. It just goes back and forth. Okay? So that's pH. That's all I have on the indicators today. And if we look at this oxidation experiment we did earlier, you'll see it's gone almost clear, sort of a nice pale brownish color. All the permanganate that was in there is gone. That's all given up its oxygen to the glycerin, given an oxidized form of glycerin, and the permanganate has been reduced. Okay? Now, we were talking earlier about explosions.
Ashkan has a question.
Oh, yeah, sure.
Can you make it explode?
Make what explode?
Like
Blast.
two chemicals and then make it.
I could, but if I showed you, I'd have to kill you.
I'm okay with it. Okay, it's okay. It's okay.
No,
okay, I'd have to
no explosions
Wait, I have
today.
another question.
We're going for safety today. Okay.
Wait, he has another question.
Okay, go ahead.
Fire. It's gonna explode on a rock.
Yes, fire. Okay, here we've got a
Mrs.
torch,
Christine,
just a
go
heat
in front
source.
because my
I don't have a
camera's-
Bunsen burner here, so we get to use a torch. Okay, we were talking earlier about how liquids and gases take up greatly different volumes for the same amount of material. A gram of water is relatively small. A gram of gaseous water, which we call steam, is much larger. Okay, so what I have here is a plain old beverage can with a little bit of water in it. Okay, just a small amount in the bottom. I'm going to heat it over this blowtorch. Okay. Now, the temperature will rise. I'm going to get the water to start boiling in there. This is an ordinary can. The top is open with just about that much water in the bottom. Nothing special. Now, as I boil it, okay, I'm going to boil off the water. The whole can is going to heat up, and we're going to get steam billowing out the top as it boils really strongly. It'll boil pretty strongly over this blowtorch because the blowtorch is really hot. In fact, the water's boiling already. I can hear it. Okay? Now, as I boil this and the can fills up with steam, just like in there with the carbon dioxide, the steam is eventually going to displace the air. And we're going to have a can full of steam and a little bit of water on the bottom. Okay? Now that's at 100 and some degrees. The water's boiling at 100. It might get a little hotter from the extra flame heating the sides of the can or something. But once we have the whole can full of steam and there's no air in there, okay, all we've got is steam. There's no air, and we've got the steam pressure inside and the atmospheric pressure outside are being equal, and the can just sits there. Now, what happens if I take all that steam that's in the can and convert it back to water? What's going to happen to the volume of the steam? It's going to condense back into water. It's going to take up a lot less space. All right? When it takes up a lot less space, okay, and we've got no more steam in the can, it goes down to water, it's going to tend to form something close to a vacuum inside the can. If we can manage to get the steam to condense all the way and rapidly. Okay? Now, there are ways that we can do this. It works really well with a sealed can, but this one's pretty impressive. Since it's a simple beverage can, you could probably get it home. Now you'll see we've got a lot of steam pouring out the top. It's boiling really strongly. What I'm going to do, I'm going to grab the can, okay, hot can full of steam. What I have here is a pan of cold water. Okay, I've got ice water in this metal can. Right? As I pick up the can, I'm going to flip it over, okay, so that the top of the can is in the water. When the top of the can hits the cold water, it's going to start cooling the metal of the can. The cooling metal of the can is going to cool steam inside, and when you cool steam below 100 degrees, it condenses to water. Okay? As it condenses to water, there's no more gas inside the can, and there's no more gas pressure inside the can to counteract the atmospheric pressure outside. Okay? So what happens then? If we've got atmospheric pressure outside and none on the inside of the can, we've got two forces, right? We've got the inside pressure and the outside pressure equal now. But when we go and condense all the steam, there's no inside pressure anymore. You've only got outside pressure. We'll have to see. Okay, so it's boiling. It's full of steam.
Whoa!
Okay? So what happens when we condense the steam? See, it's just an ordinary can. The top's open and everything. I just added a little water to it. It might still be a little warm. No, it's okay. When we condense all the steam, just the pressure of the atmosphere around it collapses the can. This is the opposite of an explosion. Okay, this is an implosion. Instead of creating a great deal of pressure from some solids and giving an outward pressure, we've taken the steam that was inside here, compressed it, condensed it down by cooling it, and created a vacuum inside the can. With the vacuum inside the can, the atmospheric pressure on the outside crushes it. There's nothing tricky about it. It's an ordinary can. I've done this on the stove at home as well, and it works just fine. All you need is a can and some ice water. Yes?
Can we try that
At home? That's up to your parents. It's definitely up to your parents. And if you don't do it right, you can make a mess dumping boiling water all over the place. So you have to be really careful. It's more fun and safer to check it out on YouTube. Yes?
Are you wearing the hat?
Am I wearing the hat?
Yeah, why are you wearing it?
Why? Because I thought you guys would be interested. Somebody even said they liked it when they came in. They thought it was cool. I'd be pretty boring if I was in an ordinary white lab coat without the hat. So, okay.
Chad, do you have
Now,
a question?
remember-
No, I was
Okay.
one of them.
Okay.
Now, we've got some things that we're going to do outside. Remember, we did the permanganate and the glycerin and water. We're going to do it outside with no water. And I have a few other cool things that I'm going to get to show you. Okay? Okay, so we're going to head outside. Don't touch any of the equipment when you go out there.
Do not touch anything outside. Just go outside and...
You bring the camera.
Do I need to take the whole thing or just take it off?
We can, I don't know, do you want to do it by hand? Let's,